Next one is analyzing air conditioning processes. The feature on the right side is showing a schematic of the system. This is a open system, so control volume system. We have moist air entering from left at the state 1, and then in the middle of this system there is an entrance, so through point number 3 here, either it is a liquid or vapor with a given mass flow, so m dot w, and then there is also a heat transfer q dot cv here, and then at the exit at point 2 we have moist air with ma, so the mass of the dry air stay the same, but the mass of the water vapor can change, so mv2. And then to analyze this process, we can apply mass balance. So first is the balance of the dry air. So we know that the dry air mass flow stay the same. So m dot a1 equals to m dot a2. And then this is the mass balance of the water vapor. So m dot v1 plus m dot w, so it's coming from point 3, equals to m dot v2. And then if we divide each term on this equation by m dot a, then we can get this equation 12.52, where m dot w equals to m dot a times omega 2 minus omega 1. And then this is for the energy balance, so we don't have work on this process. And then it is steady state, therefore it is 0 on the left side here, no w, so equals to, this is what coming in, okay, and then this is what coming out of the system. And then the enthalpy of the entering and exiting water vapor can be evaluated as the saturated vapor enthalpies at the corresponding temperature, so that we can formulate equation 12.53 to get equation 12.54, and then by introducing equation 12.52 from the previous slide, but I copied again here, then we can get equation 12.55. Okay, this is equation 12.55. So on the right side we have a q dot cv, and then the next term, so we have the term from the dry air, so we have ha1 and ha2. So these two enthalpies can be obtained from table A22 because it is an ideal gas, or table A22E for the British unit. And then the next term here we have Hg1, we have Hw. So this is the contribution from the water vapor. So Hv1 and Hv2 can be obtained from table A2, and it's equal to the saturated vapor enthalpy. Let's take a look on this example. So this is a heating moist air in a duct. Moist air enters a duct at 10 degrees C and 80% relative humidity, is heated as it flows through the duct and exit at 30 degrees C. And the schematic is showing at the bottom of this slide. So we have T1, we have V1, and then T2 is also given there. No moisture is added or removed, and the mixture pressure remains constant at 1 bar. And then for steady state operation and ignoring kinetic and potential energy change, determine first is the humidity ratio at the exit, so omega 2, and then what is the Q dot here in kilojoule per kilogram dry air. So at steady state, the mass rate balance here, I just repeat from the previous slide. So m dot a1 equals to m dot HA2, so the dry mass flow rate stay the same, and then because there is no addition and removal of the water vapor, so it's mean mv1 equal to mv2. Okay, since the mass flow rate of dry air and water vapor do not change from inlet to exit, they are denoted for simplicity as ma and mv. Okay, makes sense. Moreover, since no moisture is added or removed, the humidity ratio does not change from inlet to exit. So it's mean omega 1 equals to omega 2. So that we can calculate omega 2 from omega 1. Okay. So this is the common humidity formula here, the ratio of m dot v over ma. And then the humidity ratio is evaluated at the inlet, so it makes sense. So the relative humidity is given there. So V1 is given. And then the saturation pressure PG1 at 10 degrees C can be obtained from table A2. So by knowing V1 and then calculating PG1, we can calculate PV1. Here is the PV1, so 0.0098 bar. And then once we got PV1, we can calculate omega 1. So using equation 12.43. So this formula. So we get omega 1 of 0.00616 kilogram vapor per kilogram dry air, and this omega 1 equals to omega 2. And then the next one is calculating the heat transfer, so energy rate. So using the energy rate balance, we have this formula, and then W dot Cv equals to 0, and then we can solve the formula for getting a Q dot Cv. So this is m dot A times HA2 minus HA1 plus mv times HV2 minus HV1. And then we can also substitute this correlation so that we can get a Q dot Cv per kilogram mass of dry air here. So we have this formula. And then I write it down the equation in this slide again. So we have two terms on the right side. The first term, we can use table A22 to get HA1 and HA2. So temperature at point 1 is 10 degrees C, and then at the exit is 30 degrees C. And then for the second term, we can use table A2, and it's equal to Hg at the corresponding temperature. So we just plug in all number, so you will get the heat transfer is 20.32 kilojoule per kilogram dry air. And what you can see here, the contribution of the water vapor to the heat transfer magnitude, it's relatively minor. So it's only 0.22, and then the one from the dry air is 20.1. Next one is analyzing air conditioning systems. The next series of slides demonstrates the application of mass and energy rate balance together with property data to typical air conditioning system using the psychrometric principle introduced thus far. So we will have a look on the application on the dehumidification and then humidification, and then mixing of two moist air streams, and the last application we will see is the cooling towers. The aim of a dehumidifier is to remove some of the water vapor in the moist air passing through the units or the apparatus. This is achieved by allowing the moist air to flow across a cooling coil carrying a refrigerant at a temperature low enough that some water vapor condenses. So the picture on the right side is showing the schematic of the dehumidifier. So moist air enters at state 1, so from left side here, and then as the moist air flow over the cooling coil, so this is the cooling coil, some water vapor condenses. So you can see at the bottom here, so it is collected here. And then saturated moist air exit at state 2, okay, at state 2 here. And temperature at state 2 is lower than state 1. And then you will see later on, I believe I have one slide, we can add one more system downstream of state 2 to bring the temperature back to T1. And then back to this system, condensate exit a saturated liquid at state 3. So it is at the bottom here. And here we take T3 equal to T2. So in this analysis, we will estimate what is the m dot W over m dot A. So this is the amount of condensate exiting per unit mass of dry air. And the second one is the rate of heat transfer between the moist air and the cooling coil. And this is also per unit mass of dry air. So Q dot CV over m dot A. So first is the mass rate balance. So from this system, we know that the dry air mass flow rate stay the same. So it's mean m dot A1 equal to m dot A2, and then this is the balance for the water. So m dot V1 from state 1 from the inlet 1 equals to m dot W plus mv2, okay, plus mv2, and then solving for the mass flow rate of the condensate, we will get this formula, and that m dot W equals to m dot V1 minus m dot V2, and then with m dot V1 equal to omega 1 times m dot A, as well as m dot V2 equals to omega 2 times m dot A. So m dot A here is the dry air mass flow rate. So we will get equation 1 here, that m dot W over m dot A equals to omega 1 minus omega 2. Okay, so in this case, because it is a dehumidifier, so omega 1 is higher than omega 2. And then this is the analysis for the energy balance. So CV equals to 0, and this is steady state. Therefore, we have a 0 here. And we will have equation 2 for the energy balance. And then if we substitute this correlation along with equation 1, in the previous slide, then you will get equation 3 for the energy balance of the dehumidifier. So since heat transfer occurs from the moist air to the cooling coil, this Q dot CV over m dot A will be negative in value. So this is equation number 3, showing again in this slide. So for the condensate, we can use table A2 to get HW. So HW equals to HF. So this is enthalpy at saturated liquid. So at T2. And then option for evaluating the underlying term of equation 3. So includes first here, if we know omega 1 and omega 2. So, and then along with the given T1 and T2, so HA1 and HA2 can be obtained from, for sure, table A22, this is for dry air, while HV1 and HV2 can be obtained from the steam table A2. And then the second option is by using the respective temperature and humidity value to fix the state. So in this case, we can use the psychrometric charge to get HA plus omega times HV. Okay, so you can see the schematic on the right side here. So For example, if T1, T2, and then along with omega 1 and omega 2 are given, then we can use this psychrometric charge to estimate these two parameters. Okay, so there are two options here. Either use the value from the table, so table A22 and A2, or you can use psychrometric charge to get these two enthalpy. This is the modification of the dehumidifier. So the temperature at point 2 might be too low to be supplied back to the living room. Therefore, we put a heating coil here that will bring the temperature back maybe to T1 or slightly below T1. And from state 2 to state 3, there is no addition or removal of the water vapor. Therefore, the humidity ratio stays the same. So omega 3 equals to omega 2. And on the right side here is the schematic of the process in the psychrometric chart. So we have state 1 here going to state 2. So this is at a saturation condition. And then there will be a heating that will bring the state to point 3 here. And once again, between point 2 and point 3, they have the same omega. Therefore, point 2 and point 3 here is connected by a straight horizontal line. The next one is a humidification. So the aim is to increase the amount of water vapor in the moist air passing through the unit. So this is the reverse of a dehumidification. So this is achieved by injecting steam or liquid water. And below is the schematic. So moist air enter at state 1, and then steam or liquid water is injected here, and then moist air exit at state 3 with a greater humidity ratio. So omega 2 is greater than omega 1. And then depending whether we inject liquid or water, so T2 can be lower or higher than T1. So also for the energy analysis, we assume that there is no work and also the process is adiabatic. Okay, once again, if we inject steam, then the temperature of the moist air will increase, while if we inject liquid, the temperature of the moist air may decrease because the liquid is vaporized by the moist air into which it is injected. So on the bottom right side is showing the two psychrometric charts. So the first one is in case T2 is higher than T1, so we inject a steam. And then on the second side here is in case we inject liquid and T2 is lower than T1. On both cases, omega 2 is higher than omega 1. And then the humidity ratio and the T2 can be calculated by applying the conservation of mass and energies. And this is the conservation of mass equation. So the dry air mass flow stay the same, and then the second one is the conservation of mass for the water. And then we can get equation 1 here to get omega 2 as a function of omega 1 and M3. So this is the injected water, and then divided by MA. And then since omega 1, M dot A and M dot 3 are specified, so we can estimate omega 2 using this equation 1. This is the energy rich balance analysis. So the schematic of the system is shown on the top right figure. So by ignoring the effect of kinetic and potential energies, and then also assuming no work and heat transfer with the surrounding, then we can write the energy balance as shown in this equation. So on the left side, this is 0 because state is state. And then on the right side, we have Q dot CV minus W dot CV, and then plus this is the energy flow coming into the system, and minus this one is coming out of the system. And then W dot C and Q dot C phi are each 0, then we can simplify the equation to get equation 2. And then by introducing this correlation, like what we have in the dehumidification system, then we can simplify equation 2 to get equation 3. And then solving equation 3, then we get equation 4. So you can see in here on the left side, we have the parameter that depend on T2. So we will need to get T2. And then on the right side, we have the parameter that depend on the T1 plus whatever the condition is given in the water injection system or vapor injection system. It is 0.3 here. So this is equation 4 that we just got from the previous slide. So to get T2 from equation 4, there are two options here. The first option is by using the psychrometric chart. So the first term on the right side of equation 4, this can be read from the chart using the given T1 and omega 1. So for example, if T1 is given and then omega 1 is also given, then we have state 1 here. So this is state 1. Then we can get the first term on the right side, which is the enthalpy of the dry air plus the contribution from the water vapor. And then since the second term on the right side is known, so this one in the problem is usually known. So this one is usually known in the problem. Then we can calculate the term on the left side. So we can calculate this one. And then this value together with omega 2 that is calculated from the mass balance fix the exit state. So we have this one. If you look at on this psychrometric chart, we have this one, and then we have omega 2. Then we should be able to fix state 2, this one. Okay, once we know the state 2, then we should be able to get a T2 here. Okay. The second option is by using an iterative method. So in this case, we use table A22 to get the enthalpy of the dry air, as well as table A2 to get the enthalpy of the water vapor. So with these two tables, we should be able to get the value of this one, and this one is usually given in the problem. Then we need to do an iteration to determine what is the value of T2 so that the result on the left side equals to the sum of these two terms on the right side. So we need to do iteration until once again until this equation 4 is fulfilled. And you can imagine that option number 2 will take a longer time compared to option number 1. Next one is evaporative cooling. The idea for this cooling is pretty simple. We have moist air from the left side with a given mass flow rate, and then T1 and omega 1, and then we flow this moist air through the duct, for example, and then inside the duct we have a shock pad here. So we have water at T omega, and then there will be an evaporation of water here, so that the temperature at the exit will be lower. Why the temperature at the exit is lower? Because there will be an energy taken from this moist air to evaporate the water. And because of this water evaporation, for sure, omega 2 is higher than omega 1. This evaporative cooling is okay, especially if you have the moist air from the left side with omega 1s much lower than is needed for convenient air inside the living room. Otherwise, it is not good. If you have too humid air, it's also not good for our health. And on the right side is the schematic of the process from process 1 to process 2 in the psychrometric chart. So we have state 1 here, and then go to state 2, the omega increases, and then the temperature decreases from T1 to T2. And this is the estimated water that is needed to get a lower T2. So the water mass flow over the dry air mass flow equals to omega 2 minus omega 1, and this is the energy balance. Next one is adiabatic mixing of two moist air stream. So in air conditioning system, a frequent component is one that mix moist air stream as shown in this figure. So we have first stream here, moist air with a given m.a1, t1, and omega 1. And then on the second stream, we have m.a2, t2, and omega 2. And then the system is assumed isolated, so it means there is no heat transfer with the surrounding. And then at the exit, point 3, we have m.a3, t3, and omega 3. For the case of adiabatic mixing, we can consider how the following quantity at the exit of the control volume, so it means m.a3, t3, and omega 3 can be evaluated knowing the respective quantities at these two inlets, so at inlet 1 and inlet 2. So first is by looking at the mass rate balance. So at steady state, so we look at this mass rate balance. First is for the dry mass, so it's mean here that m.a1 plus m.a2 equal to m.a3. So it's just a simple mass balance here. And then the second one, we have the same thing but for the water vapor. And then by introducing this correlation that m.v equal to omega times m.a, then we will get equation 1. So in this case, the ratio of m.a1 over m.a2 equals to omega 3 minus omega 2 over omega 1 minus omega 3. So these quantities can be solved for omega 3 using the known value of this one, omega 1, omega 2, and then m.1 and m.2. And then this is the energy rate balance analysis. So by ignoring the effect of kinetic and potential energy, so we'll get this correlation. It's a quite long correlation here. On the left side, this is 0 because it is steady state. And then this will drop because there is no heat transfer with the surrounding, and also there is no work. So we will get equation 12.56c. And then the enthalpies of the water vapor are evaluated using HV equal Hg. So this is the enthalpy of assuming it is saturated vapor. And then with this correlation that we got from the previous slide, this equation 12.56c can be solved to give an expression with the same form of equation, the same form as equation 1. So we'll get equation 2 here. Okay, and then using the known data, this equation can be solved for this term, okay, for which T3 can be evaluated. And then if you look at the form of equation 1 as well as equation 2, we can conclude that on a psychrometric chart, state 3 lies on a straight line connecting state 1 and state 2. So this is state 1, this is state 2. So this is simple like when you do an interpolation. So you can see, you can check this correlation that state 3 will or should, or I think must be lies on a straight line connecting state 1 and state 2. Okay. Let's take a look on this example. So for adiabatic mixing of two moist air stream with the data provided in the table below, so in this table, use the psychrometric chart to determine first is omega 3 in kilogram vapor per kilogram dry air, and second question is T3 in degree C. So we have state 1 here with the given temperature, omega, and then m dot A, as well as the enthalpy. And then state 2, temperature is also given, it's lower, only 5 degrees. And then omega is also given there, and then m dot A, as well as the enthalpy is also given. So the value of HA plus omega Hg are read from figure A9 using the respective temperature and humidity ratio value. And this is the solution. The first step is to calculate omega 3. In this case, we'll use equation 1, and this is equation 1. So m dot A1, m dot A2, omega 1, omega 2 are given. So the only unknown variable here is omega 3. So by plug in all number, you will get omega 3 of 0.0074 kilogram vapor per kilogram dry air. And then we can use the psychrometric chart to get T3. So in this case, you need to map where is point number 1, okay? And then you need to map as well where is point number 2 based on the given T1, T2, as well as the enthalpy or omega 1 or omega 2. And then you need to figure out where is omega 3, okay? And then you can draw a line connecting state 1 to state 2, and then you draw a horizontal line from omega 3 going to the left that cross the line connecting point 1 and point 2, and this is state 3. Okay, and then by drawing a line vertical going down, so you will get T3, 19 degrees C. So it is simple and quick by using this option. On the second option, you can use equation 2, okay, to calculate the enthalpy at state 3. So you will get the enthalpy at state 3 of 38 kilojoule per kilogram. Okay, once you get this enthalpy, then you can draw a line along this 38 kilojoule constant enthalpy, and then until it's intersect the line connecting point 1 and point 2, and you will get point 3 here, but it is coming from this one. And then you just draw this line going down, crossing the horizontal axis, and you will get T3 of 19 degrees C. Okay, so this is the second option of getting T3. Last topic is cooling towers. Moist air principles also play a role in the analysis of cooling towers. The figure on the right side here is showing a schematic of cooling towers. So the purpose of cooling towers is to remove the heat from the working fluid of the steam power system, for example. So in this case, it is represented by the incoming warm water inlet here, this one. So this is the fluid that will need to be cooled. So it means the temperature need to be reduced from T1 to T2, say here. Okay. So and then atmospheric air enter at inlet number 3 here, and then flow counter to the falling water. So the condition is also given. So we have m dot A and then T3 and omega 3, and then to have a better interaction between this atmospheric air and the warm water, so you can see in here in the schematic, the water is introduced into this cooling tower through several injector, so that it will going down following the pattern of the injector and then forming the spray, and then will generate a lot of water droplet. Therefore, they will have more interaction with atmospheric air. And then as the liquid water and moist air interact within the tower, so this region, a fraction of the liquid evaporates. So this is possible because the incoming atmospheric air is not saturated air. So resulting in liquid water that exceeds the tower at 0.2 with a lower temperature than the water entering at 1, because there is an energy that is needed to evaporate the liquid. Okay, therefore there is a reduction of temperature here. So T2 is lower than T1, which is the objective of this cooling tower. So we want to have T2 as low as possible. Okay, and then the second impact of this interaction is that moist air that exit the tower at 0.4, so here at the top, will have a greater humidity ratio than the air entering at 0.3. This makes sense because there is an evaporation of the water. Okay, and then since some of the incoming water has evaporated, an equivalent amount of makeup water is added at 0.5 here, so that the return mass flow rate equals to the mass flow rate entering at 0.1. So we have makeup water here, so that M2 here equal to M1. And this is the mass rate balance. So to evaluate the mass flow rate of the makeup water, we can apply this rate balance to the control volume at steady state. So the first equation here is the balance for the dry air. So in this case, the dry air mass flow stay the same. So it's meaning that m dot 3, so this is the incoming moist air, equal to m dot 4. So at the exit of the cooling tower at the top side. And the second balance here is for the water. So in this case, we know that m dot w1 equal to m dot w2. Okay, the mass flow of the water, the incoming water, equals to the mass flow of the outgoing water through state 2. Therefore, this will cancel out. Okay, and then we have m dot 5. So this is the makeup water, plus m dot v3. So this is the incoming water vapor along with the moist air. It is balanced by m dot w2 plus m dot v4. So this is the outgoing water vapor through the exit number 4. And then we can simplify the equation to get this one. And then by inserting this correlation, we will get this equation to estimate the makeup water flow. So this equals to m dot A times omega 4 minus omega 3. And then we can also apply the energy rate balance to get the parameter required, for example, the T2 and so on. And we will have a look on this energy rate balance application in the next example, and I will show you in the next class meeting on Thursday. Okay, we have completed chapter 6, so this is quite long topics, and then we will continue with chapter 7 about the combustion.